right, we're on the air. We're live from Baldwin. Okay, so what is it, Saturday Night Live? It's Tuesday morning. Wake up. Well, Jay Leno can change his time to 10 o'clock, you know. All right, so what's today's topic? This. Does differentiability imply continuity? Does continuity imply differentiability? If a function is not differentiable at a point, does that mean it's not continuous there? If a function is not continuous at a point, does that mean it's not differentiable there? We have 4 questions to answer today. All right? So let's start. I'm going to start with this. Does continuity imply differentiability? Let's start with that. All right. So where is my window? Is this it? This is it. Okay. No, this is not it. This is it. So, does continuity imply differentiability? Okay, I'm going to state that as a theorem, and you're going to say, wait, you're crazy. Or you're going to say, oh yeah, right. How do you say, wait, you're crazy? How do you disprove a theorem? Proving a theorem is tough, but disproving it if it's false is easy. All you need to show is one bad example, one counter example. Can you think of a function that's continuous everywhere, but it's not differentiable at a particular point?
One where the function is important, so absolute value.
Absolute value, perfect example. Okay. So let's see. If we draw the absolute value function, y equals abs x, that was bad. Yeah, that was even more bad. Hang on. We'll wake up. Gotta wake up. Okay, so absolute value function. Sort of like this, right? It's continuous everywhere because remember the definition of continuity. I, right? Let's see. The problem is the corner, right? So what's f of 0? 0, okay. Remember the 3 conditions for continuity. F of, in this case, 0 must exist, the limit at 0 must exist, and it must be the same number, right? What's the limit from the right? What's the limit from the left? So what's the limit? Okay, does the limit match the function value? Yeah, so it's continuous, but is it differentiable there? No, because remember that the derivative is a limit. Right? And for the limit to exist, it must be the same on the left and the same on the right. Now remember, the derivative is nothing more than the slope of the tangent lines. What's the slope of the tangent lines here? 1. What's the slope of the tangent lines there? -1. Is the limit the same on the left and on the right if the limit is the derivative? The derivative on the right is 1. The derivative on the left is -1. The slopes of the tangent lines, they're not the same on the left and the right, so this limit does not exist. All right, so continuity does not imply differentiability. That's wrong. Well, what about, let's see. Okay, so let's see. If this is false, right? In other words, it's not always true. For a theorem to be true, it has to be always true, right? We found an example which made it false. So it's false. Remember, this is like an if-then statement in logic and Boolean algebra. Have you done if-then, and, or, if and only if, not, stuff like that, right? And if-then, a conditional statement is equivalent to its contrapositive. Do you remember contrapositives? If you switch the order and the sign. So we've got 2 questions answered for the price of 1. If a function's not differentiable somewhere, it's not continuous. Can you think of an example where it's not differentiable and not continuous? We had an example where it was continuous and differentiable. I want one that's not continuous and not differentiable. Can you think of something? I need a function that at a particular point, any point, give me a point. At that point, it's not differentiable, and it's not continuous. And this is not a good example because it's not differentiable, but it is continuous. Any ideas, Jeremy? Something with a vertical asymptote. Okay, let's try that. Let's see. So let's say I have a function with a vertical asymptote. It goes to positive infinity here, and let's say this is x equals 2 or something, there's a negative infinity there. It's not continuous, and it's not differentiable, because look what the derivatives are doing on this side. What's the derivative here? As they get closer and closer to the vertical asymptote, what's the slope of a tangent line? Closer and closer to no slope, or an infinite slope if you like, right? Where the delta y's would be 0, delta x's would be 0, remember the slope is delta y with delta x? Same thing over here, it goes to positive infinity, the slopes, right? So remember that the derivative is a limit, and limit, when it exists, it's a number, so infinity is bad to begin with, but it's negative infinity here and it's positive infinity there, it doesn't match. So that's discontinuous, because you have a vertical asymptote, and not differentiable. Is there any other example like that? You can think of some other example that's discontinuous and not differentiable. And there's a hole in it, look. Let's see. Let's put a hole in the graph. What if it looks like this? Something like that. Or for that matter, something like this. And maybe it's defined up here. It's not continuous, right? It doesn't pass the continuity theorem. F of, I don't know, 1 is not the same as the limit. If the limit is 4 and the function is 5 or something, right? So it's not continuous. Why isn't it differentiable? Because how do you draw a tangent line there? I could draw a tangent line that just touches the curve vertically, horizontally, at a slant, any which way I feel like. There's no one answer for what's the derivative, what's the slope of the tangent line. I can draw millions of tangent lines here. That's what's known as, that's why it's called infinity. I don't know what it is. There's infinitely many answers in this case. Okay? So that's bad too. All right. So vertical asymptote is bad for differentiability. Removal of discontinuities is bad for differentiability. And I guess that's it. All right, so now, we've talked about this is false and this is false because contrapositives. What is the, let's see, how would I write this? How did I want to write this? What is the, what's the inverse of this statement? Okay. If it's not continuous, then it's not differentiable. And what's the converse of this? If it's differentiable, it's continuous. Now notice that this statement's inverse and this statement's converse are actually contrapositives of each other, aren't they? If you switch the order, you get D, C, and you switch the sign, you get positive, positive, right? So these are contrapositives. If I can show one of them is false, they're both false. If I show one of them is true, they're both true. All right. So what do you think? Well, look, here's a good example right here. If it's not continuous, it's not differentiable, is it? If it's not continuous, it's not differentiable, is it? The same thing with the vertical asymptote thing. So this is a good example of why, if it's not continuous, it's not differentiable. So if that's true, what about this? That's got to be true too. All right. So what's the summary of this whole discussion? Remember this one. Differentiability at a point implies continuity at that point. Right? If a function is continuous at a point, it may not be differentiable there. But if it's differentiable at a point, you automatically got continuity in the bag for free. Okay? So if you got a function that's differentiable at a point, it's automatically continuous at that point. Sometimes that's a nice, easy way to prove continuity if you need to. All right. So let's see. 1, 2. Okay. Let's talk about the derivative of the absolute value function. Like we brought up a moment ago, the absolute value function was continuous at 0, but not differentiable at 0. Right? Let's see why. All right. Everyone got this? You move on? Okay. So let's take a look. Let's say f of x is the absolute value function. My question is, what's f prime? using the definition of the derivative. Okay? Well, as luck would have it, you could define this as a piecewise defined function. Can't you? What if x is negative? What do you do to it? What if I plug in a negative 5? What do you do to the negative 5? You change its sign, right? Now, technically, when you graph it, it comes out as a positive 5. But technically, that's not right. It should be no sign. But how do you graph that? So I'm going to say if x is negative, I'm going to change its sign. If x is negative, I'm going to change its sign. Otherwise, I'm going to leave it alone. Okay? That's the absolute value function. So let's apply the definition of the derivative to that. And see why the derivative does not exist at 0. Alright, so notice the function we're dealing with is different from the left at the left side of 0 than from the right side of 0. So I got to talk about the limit as h approaches 0 from the left and from the right. And I got to show that they're the same. Because that limit doesn't exist unless they're the same on both sides. So how do you write this expression in terms of this function? On the left of 0, we're using this function. To the right of 0, we're using this function. So what do you write? What's f of x plus h? What do I write? Plug in x plus h into what? Negative x. So you get negative x plus h. Minus negative x. How do you subtract the negative? You add a positive. Remember, you don't subtract, you add the opposite. All over h. Let's figure out this limit, and then we're going to figure out this limit and see if they match. All right, let's do the same thing for this function. On the right of 0, when h is positive, I'm approaching h is 0 from the right. I'm just going to plug in x plus h into x. So what do you write? X plus h minus x. Simple. Hello, how you doing? What is this? What is this? Charlie. Thank you for saying nothing. All right. Here we go. Boom, 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 boom. I guess we need a little more room. So let's do this limit. Well, what do you think you're going to do to simplify this? Distribute. Okay, so the limit as h approaches 0 from the left of negative x plus h plus x over h. Well, let's finish this side. What's... Huh? Oh, I'm sorry. I made a boo-boo. Okay. Thank you. All right, so then you get the limit as h approaches 0 from the left. What's in the numerator? Negative h, and the denominator is h. And this reduces to what? Negative 1, which is a constant independent of h. So you get negative 1. That limit is negative 1. All right, is it equal to the other side? That's the question. I'm really asking the question. Okay? All right, so what happens here? Well, let's see. You get the limit as h approaches 0 from the right. X plus h minus x is just h. And h over h is just 1. And the limit as h approaches 0 from the right of a constant is independent of h. So what do you say? Are they the same? No, not the same. So if the limit on the left and the limit on the right are not the same, and the limit is the derivative doesn't exist there. All right? And we said that. Didn't we say that when we drew it? Well, it's gone. We drew it somewhere. When we drew absolute value, right? Yeah, I sort of erased it, I think. Yeah. All right, so but we confirmed what we were saying. The derivatives on the left side were negative, negative 1 slope tangent lines, and the tangent lines on the right were positive 1 slope tangent lines, so they're different. No derivative, okay? Again, at a corner, how many tangent lines could you draw? As many as you feel like. There are infinitely many. Okay? A slope of 1, a slope of negative 1, or anything in between. 0, 0.5, negative 0.2, whatever. Alrighty, so that's an example of when the derivative does not exist. Okay, how about this one? Try this function. Let's say I give you a piecewise defined function. I don't know, g of x. It's going to be x squared when x is less than or equal to 0, and 2x otherwise. Okay? And so the question is, what's g prime of, well, the problem is at 0, right? This is a polynomial. It's continuous everywhere, differentiable everywhere. This is a polynomial too. That's not the issue. The issue is where it breaks, right? There could be a problem at 0. So what's g prime of 0? Does it exist? Well, what does that graph look like? Can you graph that without a how? All right, let's do that. All right, to the left of 0, we're doing this, and it looks like, what? A parabola. And is it open or closed circle here? Closed. Okay, because it's less than or equal to 0. So we're including 0 in for x squared gives you 0. All right, but on the right side, it's a, what shape? Line of slope 2, intercept 0. So something like this. All right, so this is the graph of y equals g of x. And there's the origin. All right, so what do you think? What's your intuition? Do you think the derivative exists at 0? Clearly the derivatives here are what? What's the slope of this line? 2. And the derivative of the parabola at that point? No. It's, well, yeah, it's 2x everywhere, but at 0, it's 0. Plug in 0 for 2x. Okay. So you know that this limit, the derivatives on this side are going to have a limit of 0, and the derivatives on this side are going to have a limit of 2, but you got to show it, just like we did. So let's do it. Let's show that the limit, as h approaches 0 from the left, is the same, or let's find out if it is, and we know it isn't. The limit, as h approaches 0 from the right. Now from the left, we're doing parabolas. So how do you write f of x plus h? It's x plus h all squared minus x squared over h, okay? And then over here, the function was 2x, so what do you write? Minus the function itself, right? All right, so let's FOIL this out. Do we need banana expansion terms for this, or do you know how to FOIL this out? X squared plus 2xh plus h squared minus x squared is still there, right? I'm just copying this part. Over h. All right, let's see. Let's focus on this side. What do we want to do next? Okay, so we get this. Let's see, we get 2xh plus h squared over h. And what happens with the h's? It's a common factor upstairs, so we can cancel it with the downstairs, and we get 2x plus h. Is that a plug-in limit now? What do you get? 2x, which we expected, yes? Okay. Is that the same as the limit on the right? I can't write. Give me a pen. The limit, as h goes to 0 from the right of this mess. What are you going to do first? 2x plus 2h minus 2x. Okay, so what do you get? What happens with the 2x? They cancel, right? We got 2h over h. What's that? That's 2. What's the limit as h approaches 0 from the right of a constant 2? Is there an h here? This is a constant. It's never changing. It's independent of h, so what's the limit? 2. All right, now, these two will only be the same when x is 1. But x is, well, what was, x was 0 was the culprit, right? So the derivative on the left was 0, and the derivative on the right is 2. These are not equal at x equals 0. Okay? Now another way to do that is to actually plug in 0 throughout. Now if I plug in 0 for x throughout, it would actually come out 0 here and 2 there. So you get the derivative at that one point, not at every single x. But I got the derivative of every single x, so if I plug in 0, it's not going to match. That's another way to do it, right? Same thing. Okay. So, by the way, you realize what this is? What is that? No. You just said it's x, right? No. This comes up a lot, especially in these kinds of problems. Plus or minus, no. I'd play with it. What if I plug in 5? 5 squared is 25. Square root of 25? 5. The x squared is in the radical. What if I plug in a negative 5? Negative 5 squared is 25. Square root of 25, or principal root of 25, there's absolute value. Okay, so we can define absolute value like we did. Or we can define absolute value like this, if we wanted to. Okay, be careful. But what's this? No, not this. What's this? Is that absolute value too? No, because if I plug in, what the hell? Let's plug in something easy. What if I plug in 25? Square root of 25. I should be specific. Principal root, the positive root, okay? What's the principal root of 25? 5 squared is 25. So I plugged in 25, I got 25. That's the same. But if you plug in negative 25, 5i. Now it does work out when you square it, does it? Yeah, it becomes a negative 5. So is that absolute value? No, it's not. So be careful. This is not absolute value. This is absolute value. Okay, you square first, then you square root, that's absolute value. You square root first, then you square, that's not absolute value. By the way, be careful. We're talking about y equals f of x only in this course. Real valued functions of a single real value. We plug in real numbers, we get real numbers. We're not going to deal with I. Okay, not until next year, yeah.
If you are dealing with I squared 5i, or would it equal 25i?
You tell me. What's 5i squared? 5 times 5?
5i.
Wait. 5i squared is 5 times 5, I times I, right?
Yeah.
So it's 5 times 5. And what's I times I? Negative 1, so you get negative 25, right? That's the problem. Okay. All right, so be careful because this comes up. So, all right, let's see. What if we do the same question about the absolute value stuff? Let's use this definition and see what happens. All right, so let's say, I don't know, f of x, whatever. I want to use h of x, but I can't because the h is running everywhere. All right, let's say f of x is the square root of x squared. All right, can you figure out f prime? And can you use that to figure out if the limit on the left and limit on the right are the same, all that kind of stuff? It's 0? Okay, let's just do this as a derivative. So f prime is what? What do you write? The limit as h approaches 0. Remember, we're using the definition of the derivative as the limit of the difference quotient, right? Okay, so what's the difference quotient here? What goes on top? X plus h all squared in a square root, right? Minus what? Rad x squared. Okay. All over h. Alright, so how are we going to deal with that? You're going to FOIL it out? Yeah, I don't know. FOILing it out is just going to make the radicand more complicated. It's going to be radical x squared plus 2x plus x squared. Does that help? What did we do with this before? We've seen this. Multiply top and bottom by the conjugate. Right, okay, let's try that. Okay, so what's the conjugate of the numerator? I'm going to quote-unquote rationalize the numerator. What's the conjugate? Rad x plus h. It's an h. Squared. What? Plus rad x squared. Okay. And if I multiply the top by this, I better multiply the bottom by this, because I know how to multiply by 1. You learned that in kindergarten. You were doing calculus in kindergarten. Remember honors kindergarten? They did it there, didn't they? Well, oh, PAG, right? Remember PAG? Yeah, they did this stuff there, didn't they? All right. Let's work this out. The limit. You were in PAG? Ah, no wonder. Okay, so let's FOIL this out. First times first, what do you get? X plus h squared. Technically, no, because I'm squaring a square root, so that's an absolute value. But I'm squaring it anyway, so it doesn't matter. What? Technically, this is an absolute value, but since I'm squaring everything, the signs are all positive, so who cares? So that really doesn't matter. All right, so first times first, then what? Outer times outer. Okay, so I'm going to say plus rad x squared times rad x plus h squared. Okay. Inner times inner, what do you get? The opposite of this, right? Negative rad x squared times rad quantity x plus h squared. And then this times this. But don't forget, a negative times a positive, negative x squared. And again, you might think it's an absolute value, but I'm squaring it anyway, so who cares? What happens to these guys? They're gone. Don't forget it's over h. All right. Now what? Equals the limit as h approaches 0. Now I think this is going to cancel. I think I'm going to want to FOIL this out now, right?
Yeah, with the bottom still being
What I do? Oh, I did that yesterday too, didn't I? Dang it, I always do that. H times stuff, right? It's a technical word, stuff. Look it up in the glossary of the textbook. It's stuff you don't want to talk about. It's stuff you don't want to say. Okay, so yeah, is that what you were saying? I was missing this? Oh, it gets so sloppy. So what happens to this thing? I think I'm going to FOIL it out, because think ahead. What's going to happen? It's going to go away. All right, so it's x squared plus 2xh plus h squared minus x squared in the numerator. And stuff. All right, I think I need some more room here. So the x squareds cancel on the numerator? Okay, the limit. One step at a time. Show all the steps. Do yourself a favor. If you skip steps or you do too many steps at once, you're likely to put your foot in your mouth all over the place. So it's not good. Whoops. The conjugate, negative. And the h is canceled. It's a common factor up here, so it cancels, and you get, how about if I put it here? The limit as h goes to 0. All right, so what's left in the numerator with a factor out the h? 2x plus h over this conjugate thingy. Okay, I need more page. Okay. And it's, wait, hang on. Plus, 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 you're right. Oh, it's still learning. I'm learning to do the calculus thing. Okay, so here we go. First period calculus, that's murder, man. And it's supposed to be more murder for you guys. You see ninth period, they're like punch drunk by the time they get to me. I've had like 50 other APs already, and they're like off the wall, jumping around, screaming and yelling. It's crazy. And it's only 8 kids. All right, now what? What was that a plug-in limit for h going to 0? Yeah, okay, so let's see. It's going to be, well, I plug in h equals 0 and I get 2x in the numerator. And what do I get in the denominator? 2 rad x squareds. Aha, the 2's cancel. And the rad x squared is, yeah, well, hang on. When I plug in 0 here, I get rad x squared plus rad x squared. So I have 2 of them.
Oh, yeah.
Okay. All right, but remember what this is. Absolute value. So we're back to absolute value again. What did we do? Nothing. We ended up with the same problem. All right, now, no, this is the derivative though. We realize that the derivative is different on the left and different on the right. What if I plug in a value like, I don't know, 5? I get 5 over 5 is 1. Wasn't the slope on the right positive 1? It's still the absolute value function we're doing, right? What if I plug in a negative 5? It's negative 5 over 5. So it's still negative 1. So the limit on the left and the limit on the right are not the same. Ah. Okay, so I could still, well, I don't know if I want to make that argument, but you could show that the limit on the left, okay, this creature is x over absolute x. That's what it is. This whole thing. And the limit on the left is different from the limit on the right. So on the left it's negative, on the right it's positive. In fact, could you say this? No, you can't say that. Sorry, that's a lie. Yeah, no, I'm sorry. No, because then it's not 1. Yeah, whoops, sorry. I went a little too crazy. Okay. No, that's it. That's the derivative of the absolute value. It involves the absolute value. What can I tell you? Yeah. From here to here? Look, if you plug in 0 for h, you get 2x on top, right? But if you plug in 0 for h here, you got x plus 0 is 0, and, x plus 0 is x, and x squared gives you rad x squared plus rad x squared. You just got 2 rad x squared. So the derivative of the absolute value involves the absolute value. That's why the derivative on the left is positive, and the derivative on the right, I said it wrong. The derivative on the left is negative, and the derivative on the right is positive, so the derivative doesn't exist at 0. Okay, good. There you go. All right. I did that. All right, let me save here because otherwise I'm going to screw up next period.